One of the very nice features about linear algebra is it combines algebra and geometry in a very nice way. And the equations in linear algebra have a geometrical intuition. I want to talk a little bit more about that in this video. All right, so these are the topics I'm going to talk about. First, the parametric description of lines, planes, and hyperplanes, which is in Chapter 5, I believe. Second, the geometrical nature of dot product. I'll explain this comment later. Preservation under distance-preserving transformations. And then the dot product representation of hyperplanes, the geometrical and algebraic significance, and then multiple dot product conditions. All right, so let's begin. Now, we saw in the chapter that a line can be represented as the set, let's call it P, plus t times u. And here t can be any real number. Okay, you see? So this is not an arbitrary linear combination of p and u. This is a fixed vector p. And then it's a multiple, or you could say it's a linear combination of one vector. So this is a multiple of a single vector. So here's this scalar, and this can be arbitrary. So it's changing. I allow any value of t, and then this is a fixed vector. So geometrically, what does this mean? Well, you're adding two vectors, right? And here, this vector can be scaled arbitrarily. So I'm going to call this vector here u. And the fact that I can scale u arbitrarily means u can be scaled as much as you want. Now let me just say that when you think of a vector, you should think of a direction. You shouldn't think of the vector necessarily coming from the origin. Vector just indicates direction in general. All right. Now, I'm going to eat my words right here, because in this representation of line, P does represent a vector from the origin to the point P. So this vector here represents P. All right. So you can think of this as going out from the origin along the direction of P. All right. And then what am I doing? I'm adding a scaled version of this vector u. Okay. So if I take P plus u, right, then that will take me from here out to here. Right? Because you add vectors head to tail, P first and then u. So this is P plus u. If I have P plus 2u, then I go out P, and then instead of going out 1u, I go out 2u. So this would be P plus 2u. If I wanted P minus u, instead of going out in this direction, I go out in the other direction. So this one here would be P minus u. Okay. And then P minus 2u. Okay. All right, now, so we can see that we really are getting in 2 dimensions something that looks like a line. Now suppose you did this in 3 dimensions instead of 2 dimensions. Right? You'd really get the same picture. I could try to draw my 3 dimensions here. Right? And then P would be some vector out pointing out in space in some direction. And then if I choose another direction somewhere out in space here, and that's my u, and I add P to scaled versions of u, then I will get a line like this. Right. So this is tu. Now, suppose I don't just allow going out in one direction, but I allow going out in 2 directions. Okay, so I can say P plus, let's say, tu plus sv. All right, where t can be an arbitrary element of the real numbers, and s can be an arbitrary element of the real numbers. So what does this look like? Well, think about what this means again. Actually, I can have the picture down here. Here's my P going out here. Here's my u. I'll make my u my green one again. Now P plus t times u is going to be this same line All right? And if this is my v, then if I go p plus s times v, that will give me this line. But if I take p plus t times u plus s times v, I can go out this direction first and then parallel to this direction. So this here would be, if I go up p, then u, then v, then p plus u plus v would be here. P plus u plus v. And you can see I can do any combination. I could do p plus u minus v. I could do p minus u, p plus u minus v would be down here. I could do p minus mu minus v, etc. I can actually get in all four quadrants of this axis determined by u and v. All right, so you can kind of see I've tried to map out that this yellow, this entire plane, corresponds to that parametric set. Okay, let me move on to the second topic, which is geometrical explanation of the dot product. I wrote this all out because my tablet was acting up. Now, in the book, you have this formula for cos theta equals u dot v over length of u and length of v, where u dot v is written in this way, u1 v1 plus dot 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 plus u n vn. Okay, and here's the picture. U is this way, v is this way. Here's the angle, and the cosine of this angle is equal to this dot product divided by these two lengths. Now, why does this make sense? Well, let's work our way up from 2 dimensions. In 2 dimensions, this formula looks like u1 v1 plus u2 v2, where these are the two components of u and v. So in 2 dimensions, where does this formula come from? Okay, let me see if I can move this over a little bit. I had to zoom out to fit it all in. All right, so you remember the law of cosines. You should have seen this in pre-calc, where you have A, B, C, 3 sides of a triangle, and the angle here, let me just draw it in, the angle here, I will call this angle phi, and I'm calling it phi for a reason that you'll see. Now, law of cosine says that a squared plus b squared minus 2ab cosine phi is equal to c squared. All right, let's see if we can transfer this into vector form. All right, now I can think of a as a vector, so I'm going to call a u. So I'm going to turn this into a vector. And I'm going to call b minus v. Now there's a reason why I call it minus v. Okay. All right, and then c I'm going to draw this way. Right. Now, how do you get c from a and b? Well, I have to take the vector from b to a, and that's the same thing as taking a minus b. Or in other words, I'm saying u corresponds to a, minus v corresponds to b. So I'm taking this vector, which is u, subtracting this vector, which is minus v, and I get u plus v. So c is u plus v. So the correspondence is a is u, b is minus v, and c is u plus v. Now, if I translate this law of cosines into my vector notation, I get a squared is equal to the length of u squared. B squared is the length of minus v squared. And 2ab is 2 times the length of u times the length of v times the cosine of phi. And c squared is the length of u plus v squared. Okay, so I've done straight translation of my law of cosines from trigonometry into vector notation. Now, one thing to notice here is that the length of minus v squared is the same as the length of v squared, because the squares of the components of minus v are the same as the squares of the components of v. All right, so I can replace this length of minus v squared with the length of v squared. Now, we also know from the Pythagorean theorem and the extension thereof that the length of u squared is equal to u1 squared plus u2 squared. Etc. Length of v is v1 squared plus v2 squared. And I can also get the length of u plus v as u1 plus v1 squared plus u2 plus v2 squared. So I've done the substitutions here. u1 squared is here. Negative v squared is here. I've kept this term the same, and u plus v squared is here. All right, so I've got this algebraic equation. Let's go ahead and write this out. And I get the cross term, which is 2u1v1. Apart from that, I have the u1 squared and the v1 squared, but those cancel the u1 squared and v1 squared on this side. Similarly, I get u2 squared plus cross term plus v2 squared. The u2 squared, v2 squared cancel on this side. So after I do the cancellation, these all go away. The only thing left on this side is 2u1v1 plus 2u2v2. And I get that's equal to minus 2 times length of u times v, length of v times cosine of phi. So then I solve it and I get minus cosine of phi is equal to u1v1 plus u2v2 over length of u times length of v. And of course, this is my expression for u dot v. Okay. Now, what's the problem? We've got a minus here. Why is there a minus there? Well, now we see why I did this funny business with minus v. Okay. This is the angle between u and minus v. All right? It's the angle between u and minus v. Now, where is v in this picture? Let's go up there and find it. Okay. V is pointing out the other direction. Okay. So v points out this way. My theta is this angle here. I'm not going to draw it I don't want to mess up my picture, but v is this way because v is the negative of this vector. And the angle theta is this angle here. Now this angle here plus this angle is pi. So theta is equal to pi minus phi. All right? So the theta, which is the angle between u and v, is pi minus v, pi minus phi. Now if you work out your cosines, that means the cosine of theta is minus the cosine of phi. So I can substitute minus cosine theta for cosine of phi. And I get this here. All right, now this works in 2 dimensions. What about higher dimensions? So how about dimensions greater than 2? Notice this fact. Any rigid transformation, that is a transformation that preserves lengths, also preserves dot products. Now what do I mean by transformation? I mean a function that moves things around. If I move things around and I preserve the length, I'm also going to preserve dot products. All right. You can imagine a rigid object. If you move it around, the different lengths don't change. The sizes, the shape, it's completely the same. So all lengths between any 2 points on that object remains the same. So why is it true that a rigid transformation preserves dot products? Well, if I take my 2 vectors u and v, and I form a frame from them so that the lengths don't move, okay, that means also the lengths between the 2 tips can't move either. So if I have u here, and I have v here, then this length here from here to here, that also can't change. Okay. Now the length from u plus v or u minus v, it's the same thing. I can call this minus v, and then this length is going to be u plus v here. U plus v. All right. So none of these lengths can change under my transformation. Now u plus v squared can be expressed, as we saw before, as the length of u squared plus the length of v squared plus 2 times the length times u dot v. Now on my transformation, as I move this triangle around, this length's not going to change, this length's not going to change, this not going to change, so this also is not going to change. So how do I know that this dot product gives me the angle in higher dimensions? Well, I can take my triangle and rigidly rotate it out of 2 dimensions into higher dimensions. You can see that in 3 dimensions. Make a triangle out of paper, put it on the plane, put it on your table. If you take it off the table and throw it up in the air, it's still a triangle. That's a rigid transformation. I'm moving it out of the plane into space. And so as I do that, those vectors I could express in 3-dimensional coordinates. Those vectors will change, but it's guaranteed that the dot product between those vectors will not change. Okay, so the dot product is characteristic of the basic geometry. I can put these 2 vectors in the plane in 2 dimensions, I could put them in 3 dimensions, and I could put them in higher dimensions as well. And that's not going to change the fact that the dot product gives me the cosine between the 2 vectors. All right? So I can rigidly rotate and it won't change. Okay, now what's the relationship between dot products and planes? And I actually should say hyperplanes. Okay. Now, we've talked about how a dot product corresponds to the cosine of the angle. Now, suppose the dot product between u and v is equal to 0. Well, remember, dot product between u and v is proportional to the cosine of the angle. And the constant of proportionality is always positive as long as u and v are non-zero vectors, because the proportionality involves the lengths of u and v, which are non-zero if u and v are non-zero vectors. So the only way for u dot v to be equal to 0 is for the cosine of the angle between them to be 0. If the cosine is 0, that means theta is 90 degrees pi over 2, or it could be 3 pi over 2. But anyway, we can conclude geometrically that u and v are perpendicular. And this conclusion holds in any dimension, because as we said, the angle doesn't change if we rotate u and v into higher dimensions. All right? So this important fact that u dot v equals 0 means that u and v are perpendicular geometrically. Algebraic specification, geometric fact. All right, now we can now consider the equation n dot x equals 0 for a fixed vector n and for variable x. We want all vectors x that satisfy this condition. And we'll look in 3 dimensions first, but the conclusion holds for any number of dimensions. Now, x satisfies this equation if and only if n is perpendicular to x, as we've seen. So the set of solutions of this equation are the set of all vectors that are perpendicular to n. Okay? So I'm going to draw my vector n here, and any vector that's perpendicular, like this one, is in the solution set. All right? And you can see that all these directions perpendicular, in fact, you could imagine holding a fixed rod here, then taking a vector perpendicular and twirling it around like an umbrella, only perpendicular. And all these vectors that get twirled around to are perpendicular vectors. Now you see that this set specifies a plane in 3 dimensions. All right. Now, we go back now to the algebraic expression of dot product. The algebraic expression of n dot x is n1x1 plus n2x2 plus n3x3 equals 0. Now this is a system of linear equations. Even though it's just one, it's still a system. So let's solve it using our usual methods. The augmented matrix for this system has just one row, n1, n2, n3, and then the constant is 0. Now if I RREF this is an example where the augmented matrix is so simple it's difficult to think of the augmented matrix. But the augmented matrix simply changes this first n1 into a 1. So as long as n1 is not 0, this is the REF form of this vector, this linear equation. Now, if n is 0, then it's similar. You just get a 0 here, and then you get a 1 here. But the conclusion is basically the same. Now, if you write the solution to this system in our usual way, you can see the system has 2 free variables. So that gives me 2 parameters that I can vary to find the solution. Now, if you work this out in the usual way that we've always solved linear equations, you get this solution for your 3 components of the vector. I'm using x1, x2, x3 instead of x, y, z, but the idea is the same. x1, x2, x3 is equal to any arbitrary constant times this vector plus any arbitrary constant times this vector. And you can work these out and see that this is correct. You can also verify that this vector is perpendicular to n1, n2, n3. Just take the dot product and see. This vector also is perpendicular to n1, n2, n3. Okay, so my solution set is an arbitrary linear combination of 2 vectors. And we saw before that that's a plane. Okay, so we saw geometrically that this should be a plane, and we see algebraically also that this solution set should be a plane. All right. Now I can use the very same argument in n dimensions. Okay, if I take n dot x equals 0, where n and x are n-dimensional vectors, I'm using a big N for the dimension to distinguish from the little n, which is the vector, then that will give me a linear equation which I can consider as a system of linear equations with n minus 1 free variables. Since it has n minus 1 free variables, the solution set is spanned by n minus 1 vectors, so it's an n minus 1 dimensional hyperplane. It's the set of all vectors that are perpendicular to some fixed vector in n-dimensional space. Now that's an n minus 1 dimensional hyperplane. If I want to get lower dimensional hyperplanes, then just add more perpendicularity conditions. Say your vector has to be perpendicular to n, and also to m, and also to q, and also to w, etc. Each time you add another perpendicularity condition, you will reduce the number of free variables by 1, and that's going to reduce the dimension of the hyperplane by 1, right? Because the number of free variables is the same as the dimension of the hyperplane. All right, one last comment. We've done n dot x equals 0. What about n dot x equal a, where a is a constant? Okay, that's also a possibility. Let me find the solution set, that is, the set of all vectors x that satisfy this equation. Well, let p be any solution, so I'm going to take one particular vector that satisfies this equation, and that should be easy to find. Just take a vector, take its inner product with n. If it's not a, then multiply p by a and divide by the length of p, and that will give you a vector whose inner product with n is a. All right? Then I can rewrite this equation here. Can't even see my mouse. I can rewrite this equation here as n dot x equals n. I'm sorry. I can rewrite this equation here as n dot x equals n dot p, because n dot p is equal to a. And then I can rearrange this to say n dot x minus p is equal to 0. Now I'm back in business, because I know n dot something equals 0 means that n must be perpendicular to this vector x minus p. So what's the geometrical significance of this? Well, p is some fixed vector here. If I take any vector x, then x minus p is the difference vector. So this equation here is saying that x minus p is perpendicular to n. So for any fixed vector p, take x minus p has to be perpendicular to n. Now this is a plane that contains p. Notice that this is actually a particular solution. My p is a particular solution. And here I'm getting a homogeneous solution. My x minus p is a homogeneous solution. So this is a whole other picture of particular plus homogeneous. Okay. The homogeneous corresponds to a plane through the origin, and the particular vector shifts it out away from the origin, and I get a vector, a plane through p. Now you can see that there are many vectors I could choose for p. I could choose p here, I could choose p here, I could choose p to be any particular point on this plane. No matter which point I choose on this plane, it will still be true. If I choose this point here, it will still be true that if I take another point on the plane and take the vector joining them, that's going to be perpendicular to this normal vector. Okay? So all of these vectors in here, you take differences of any two vectors in here, it's always going to be normal. So that's the kind of set this is. It's a plane that's perpendicular to n that passes through the particular point p. All right, so hopefully that clears some issues about relating geometry and algebra to linear algebra. Hope you enjoyed this series.